Okay, does everybody have an index card?
Yes.
Alright, most of your work today will be done on this index card. We're actually going to be stepping back into some of that computer theory that was left off 2 weeks ago. Remember I was teaching you guys how to count and learn what binary is all about. In this exercise we're going to be using some of what we've learned back in week 1. We're also going to be venturing into something new. We're going to be learning how a computer processes data. In fact, we call this digital processization, okay? So we're going to be taking information, coding it into a binary format, which we've come to call data, okay? Remember, there's a difference between data and information. Information is what you and I care about. Data is how a computer sees the information, how it's stored, how it's going to be retrieved. You okay about that? So we took this complex counting system, base 10, and we managed to take it all the way down to 2. Remember, when we're learning how to count, the idea wasn't really counting, but rather the 3 rules that we established. We first create a base. Remember, the base just consists of symbols, unique symbols. You cannot have 2 same symbols in your same base. In other words, the symbol that represents number 1 can only be used once, correct? 2 has a different shape to it. 3 looks different than 2. Same thing with 4, right? They're all unique. Your base can be whatever size you want to make it. When it comes to computers, we decided to make our base 2. Why? Because the computer doesn't see 1s and 0s like you and I see it. In fact, that's only there for us to understand how we can teach a machine to process information. In fact, that's what today's exercise is going to be all about. Us watching how a computer processes information. And that's what you're going to be doing on this index card. You're going to be acting like a computer today. It's going to be very counterintuitive, because you're just going to want to write everything the way you store it up here. Which is also interesting, because the way you store something up here is the way you were taught to do it. Remember back when you learned your alphabet? You were forced to memorize and not to understand. And when you're a kid, your mind absorbs this like a sponge. You pick up on things really, really fast. They say the best time to teach somebody a new language or a foreign language is when they're what?
Kids.
Young. Why? A language is a very complex, abstract concept. And that's all it is. It's just a concept that we use to communicate with. Can we use something else to communicate? Have I been using something else to communicate with you guys in class? My visual aids, the whiteboard, the projector. What else can we do to communicate?
Sign.
We can sign language. We can probably even use touch. I mean, doing things hands-on, interacting with an exercise like you're going to be learning today. So today I'm going to be using several means to teach you. Visually, of course, auditory, right? You'll be hearing it. And you guys are going to be doing it. So I go back to this concept of a number system. And what does that have to do with anything coming with computers? Well, like I said, computers don't see 0s and 1s. In fact, the way they represent 0s and 1s comes in many different formats. The most common representation of a 0 and 1 is electricity. I go back to testing a 9-volt battery. What's the classic way of testing a 9-volt battery? Yeah, you don't put it on your tongue. If you got a younger brother, you put it on your younger brother's tongue. And if you get a reaction, then you know something, correct? And if they don't have a reaction, then you know the battery's dead. Or they're really, really good at hiding that reaction. I wasn't the youngest one in my family, but I was the scrawniest one in my family, so I became the battery tester. And over the years, you start to develop some kind of resistance to the battery. And then you get to the point where you just hold that urge back and say, battery's dead, go ahead, you try it out. And then you run like hell, right? But that's the process. Do you see how we use something else to symbolize? The wise thing to do is to buy a voltmeter or a battery tester, correct? And what does it gauge? How much energy is in that battery, if you will? Well, that's all a computer is. It's a glorified voltmeter. In fact, we decide to say, when the value is at this level, it's a 1. And when the value is at this level, it's a 0. Could I do that any other way? Can I do something else instead of using electricity to represent those zeros and ones? Remember, now we're moving away from those zeros and ones as being ways to quantify something. Quantifying meaning that I have 15 students, right? Because all they are is just symbols. That's it. We can make those symbols represent something else. Like 0, no electricity. Like 1, electricity. Does it matter the amount of electricity? 0, no electricity. 1, any electricity. Just give me something. When I was counting with my fingers, instead of them representing each number, like I have 2 fingers, I decided to use their position, up and down, correct? What else could I use to represent zeros and ones? Remember, they have to be distinct, and they cannot be one value and at the same time be the other value. Classic example, you can't be standing while you're sitting, correct? The lights can't be on while they're off. That's what we mean by discrete. Remember, uniqueness can only be 1 at a time. It can only be a 0 or a 1. You good about that? What else could you guys use? I gave examples last week. Think about distinct values that we can manipulate and change. As I survey the classroom, I sort of have like a half and half. I have 1, 2, 3, 4, 5, 6, count myself, I guess, 7. And I have 1, 2, 3, 4, 5, 6. So it's about 6 what and 6 what. My base could be M for male, F for female, correct? Now I have 12 of you. But I gotta cut it in half because I have 6 boys and 6 girls, correct? So that means I have 6 bits, and I can interchange them with boys or girls. And I can arrange them in such a way by grouping them to say that when I get a girl, girl, boy, boy, it's going to be the letter A. And then when I get a girl, girl, boy, girl, it'll be the letter B. And then when I get a girl, 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 boy, it'll be the letter C. Remember how we learned how to count? What else could I use? The lights? What about sound? Could I use sound? No sound? Sound. Correct? Or it could be the difference of a cough and a clap. Just as long as you can't cough and clap at the same time. So maybe the clapping is the same. What else? What about magnets? Could I use magnets? North and south. Base 2. We take this simple system and we bring it all the way down to only represent 2 values. And these 2 values we can use in pairs, in groups, to represent large amounts of data. This data can be processed to represent color, sound, letters, possibly scent. How about touch? Right now, all we're doing is addressing, 2 out of our sense? In the future, mark my words, you'll be licking your monitor. Well, at least some device. That'll give you the ability to taste. And you're like, why would I want to do something like that? Doesn't it add another dimension to video games? Maybe another dimension in entertainment? Movies? Yeah. Well, we could go many different places with this, but let's hold this tasting thing aside, and let's look at smell. You guys want to smell something? I have a younger brother and he's loving this. In fact, like I said, I was the scrawniest one in my family. When you're the little guy, yeah, you get treated quite differently. And my younger brother would send me an email that would have some special fragrance of him. Use your imagination. And that would be a different type of junk mail, wouldn't it? Should we digitize scent? Could we? What would the process be if we wanted to? Now you guys are thinking, I don't know if I want to smell something. But if you're an avid video gamer, what's the drawback right now that we have in the games that we play? It's two-dimensional, emulating a three-dimensional space, correct? You can't see behind you. In fact, when you're playing this in real life, whether it's laser tag or paintball or whatever, you get that sense of aura that maybe somebody's watching you or somebody's following you. Granted, you can probably hear their footsteps. And video games are getting better with surround sound. But there's something else. Like somebody who hasn't taken a shower for a week. Something else. If you add that to the game, that gives you an advantage. What about touch? Games are trying to become more realistic, but there's a certain reality that they lack. You can't be firing a million rounds without having some kind of consequences. Like the gun over here. What about movies? Another dimension into the movie. To feel that person's skin takes a whole nother level to romance. Their fragrance. Trust me, marketing people would love this. Does anybody buy cologne online? What about t-shirts that could have fragrance built into it that could either reflect your mood or it can change when you change? You don't have to buy a gallon of that crap that you get sick of after 2 sprays. Now when Calvin Klein sells you a pair of jeans, their fragrance comes with it. Clothes will always smell brand new, even if they haven't been washed for a decade. Bless you. And what about the opposite? As we're looking back at this, we're saying, I don't want to smell that. But what if you can't smell? What if you can't taste? What if you can't see? And what if you can't hear? What if we can make devices, instead of converting that stuff into binary, converts it into the way you and I perceive data? Because what we see isn't what we store. I see light, but that light is processed into a chemical reaction that's stored up here. And if I knew the code, if I knew the DNA that represents this classroom, the smell, the sound, the light, the touch, then I can make devices that I can wear that allow me to hear, taste, smell, and see. And that's the level we're at with computing. We asked ourselves, are we done with computers? How much more faster can we make these things? Look at our need. A tablet is doing just fine for our everyday usage. But we need to justify jobs. We need to give people a problem. Otherwise, we get bored. So we take this concept that you guys are learning right now, and we're applying it to making ourselves live forever. And it's right around your corner. In fact, they say your generation has the potential for living for thousands of years. Would you want them to live for that long? I'll leave that up to you, just like whether you want to turn on the nose button or not on your video game. So the question is, can we make that possible? Let's see how we can do it. I want you guys to do with your index card. Got it right up on my board. I want you to take your name. Remember, we're going to start, and I'm showing you the process of visualization. So we're going to start with something nice and simple. We're going to start with letters. All right? The same process can be applied to sound, scent, taste, and light. Now, when I refer to light, I'm talking about color, right? In fact, the only thing a movie is a bunch of pictures with sound linked to it, correct? So we'll talk about that. But for now, I want you guys to take your index card, and I want you to write your name, full name, including the space, and make sure it's in proper checks. So I wrote my full name, capital N, lowercase, the rest of the letters, then I put a space, then capital letter A, then the rest of my letters for my last name. So we're doing something that we're very familiar with, writing, right? Using this instrument. Why do we write things down?
It's a reference. People look at it again.
To store it. Because sometimes you question this, correct? Why do we have a problem memorizing things? This is very unnatural. It seems natural to you guys, but if I start writing it in Swahili, would you be able to read it? So is it natural? Now, if my brother let one go, whether it's in Iraq or in his classroom, would both countries be able to understand what happened? Is that natural? So why does everybody have a problem with it? No, I'm kidding. See, I'm just trying to help you guys. Yeah, you guys have a problem with it. All right. Letters are unnatural. We developed it. It's a language. They're just symbols. The letter N means nothing. But when I group it with Nicholas, it might have an association. And you might associate it with me, or maybe another Nicholas in your life. Correct? That's the problem with memorization, is that we try to memorize things that make absolutely no sense to us. And your key to understanding something is convert it, translate it into something you understand. You might just call me the bald guy in front of my classroom, and you'll remember that. In fact, people tend to remember faces a lot more than they do this. Ironically, computers do the opposite. Images are a lot harder. In fact, visualization, we can retain up to 70% of it because it's natural. When you're first born, you see objects. Underneath your name, I want you to write this heading. We're going to spell it as C-H-A-R. Then we're going to go vertical here. And I just want you guys to use the very first, let's do 4 letters of whatever you wrote up here. So watch what I'm going to do. Capital letter N, lowercase I, lowercase c, lowercase h. I'm just going to stop right there. So I took this word, this name, and I broke it up into characters, correct? Remember, the base for our system would be from A to Z. You good about that? Now, capital letter appears different. In fact, the computer has to store entirely different. You and I see it as just the letter N, right? and the state's different. It's like a book and a man, if you will. Alright. The question is how do I take these letters and digitize them? How do I take sound and digitize them? How do I take light and digitize it? Well, just like what we did when we started counting, we had to develop the base. We know our base for our system is going to be A through Z, correct? 26 letters. But wait a minute, I just got done saying that a capital letter is different than a lowercase letter, correct? So how many letters are in our system?
52.
52. Is that it though? See, my last name has a special character. For the longest time, we had to acknowledge that when it comes to computing. We just said, hey, look, you want to be fancy, you can be fancy on your own time, but we'll just treat it like a letter E. Other cultures wasn't too happy about this. We'll explain that when we get to that code. But our alphabet also consists of numbers too, right? In fact, look at your keyboard. Do you see all your keys on your keyboard? It's probably about 101 or so keys in your keyboard. You notice you have like 0 through 9 up top, then you have minus, plus, parentheses, the @ symbol, the pound, and so on and so forth. Well, we said that, you know what, there's about 136, give or take, characters that represents our English language. Good with that? Now I say our English language because in our language, that's what we use to represent currency, the dollar symbol, right? But in Britain, they use the pound, which is another symbol. Looks like a fancy L, if I remember correctly. Getting the idea? So we developed a standard in this country called ASCII. It's the American Standard for Character, Information, Interchange.
We're supposed to write down on
No.
okay.
This is just me letting you guys know that we're going to use this. In fact, the way we're going to use this is that if you guys were to log on to Blackboard and go to week 3, I gave you a little ASCII chart. When you guys go on the Blackboard over here on week 3, you have a little chart. Click on that. You might need to zoom in. But if all goes well, do you see how I took a decimal number and I mapped it to some letters? And this is completely arbitrary. But what we had to do is we had to agree upon this. We had to make this standard that every computer in this country is going to be able to understand this table. So that all computers, when they read a text file, they interpret it correctly. Does that make sense? Just like when you were a kid, being that you were born in this country, they taught you this language. Computers have to be taught. And this is the first thing they are taught. This is the first thing they are taught when they boot up. What a letter is represented by. Now some students ask, why is the letter A at 65 and not at 1? And my question to them is, what would you make the number 1? Because all those symbols that are on your keyboard have to be represented, correct? So wouldn't it make sense to make 0, 0, 1, 1, 2, 2, 3, 3, right? So then why isn't the letter A 10 then? I'll show that at the end of this exercise. But for now, let's just accept that the letter A is 65. A space is 32. Interesting. We'll get there later. B is 66, C is 67. So what I'm going to do is I'm going to go back to my index card. And I'm let's see, you guys can help me out here. Obviously I have my screen on something else. What was the capital letter N?
78.
78. So what I'm going to do is I'm going to come over here back on the second line, and I'm going to write DEC, short for decimal, right? And then right next to my letter N, I'm going to write 78. Who wants to be the teacher's pet? This letter I.
73.
Lowercase I. You might have to scroll down. 105? 105? Letter C?
99.
And letter H?
104.
104. Well, that sort of makes sense, right? Because you're following the alphabet H, I, J, K, L, M, N, P, right? Alright, so you do the same. Map your letters to a number. Do you see how we're all following the same table? But see, a computer doesn't understand decimals. The only thing a computer can understand is how to turn switches on, how to flip the polarity of a magnet, possibly how to show you light and not show you light, if you will, turn light on and off. So, here we are. We need to take it to the next level. We need to be able to take what we entered in our keyboard and display it as data. So let's go back on the row, second row, and let's type in bin. Bin's short for binary. We need to take this decimal value and convert it into binary. In other words, I need to teach you something. I need to teach you how to convert decimal into binary. Now, of course, your keyboards, they automatically have this binary stuff hard-coded into that. Remember, today's goal is to understand how data is being processed, or how information is being processed into data. You good about that? Alright, there's two methods. One's really quick, and the other one's really slow. Which method do you think I'm going to teach you?
Really good.
That's the method you'd like me to teach you. I'm going to teach you the slow, misery, painful one. There's a reason behind it, and I want you guys to be entertained for a second. All of your work from here on out to convert these numbers are going to be done on the back side of your index card. You guys are going to flip it over, and you're going to be flipping back and forth. The method I'm going to teach you is called the division method. How many numbers make up binary? Just two. When you take any number in the world and divide it by 2, there's only 2 possibilities you're going to get for a remainder. Throw me a number out there. Any number.
23.
What's that?
23.
Okay, the remainder is going to be 1. Throw me another number out there.
22.
Remainder is going to be 0. Any number. Make it large.
1,578.
0.
Yeah.
Give me another number.
617.
617, you said? Odd. Oh, sorry, 1. Oops, I gave myself away. When you divide a number by 2, you're going to get a remainder of either 1, and if you get a remainder of 1, the number was odd. If you divide an even number by 2, that means it can be split in half evenly. You'll get a 0. Do you see something going on though? I'm only ending up with 2 values, a 0 or a 1. So let me demonstrate how you guys are going to convert your decimal number into binary. I'm going to take my 78. I can do it right there. That'll help. You're going to do it on the back of your card. And I'm going to take that 78 and I'm going to divide it by 2. Right? What am I going to get? Let's see. 39 remainder 0. I'm going to take this 39 and divide that by 2. What am I going to get? 19 remainder 1, is that right? I'm going to take that 19 and divide it by 2. Odd, odd, I'm getting 1s. Even, I get a 0. I'm going to continue this process until when?
Until you get down to 2 or 0.
Until you get down to 0. And then I'll have to move this up over here. And I have to do that 0. When you divide anything by 0, right? Let's count these. 1, 2, 3, 4, 5, 6, 7, 8. A couple weeks ago, I told you that one byte represents 1 letter. How many bits did I tell you made up a byte? 8. How many remainders did I get? 8. You start with the lowest one, and you string them up. So 78 in binary is going to be a 0, a 0, a 0, a 0, a 1, a 1, a 1, and a 0. Start at the bottom, glue these numbers together, and this is what you get for 78. Now students like that method. It's slow, it's very tedious, but it's simple. Divide by 2 and keep on dividing by 2 until you end up with a 0 there, correct? This does not tell you that a computer has this stored as zeros. What it's telling me is turn this switch off, this one on, this one on, this one on, this one off, this one off, this one off, this one off. If I wanted to represent the letter N in my computer, I needed 8 bits. You guys are going to convert every single one of your letters into binary. You're going to do that work right back here. You're only allowed this card, so make sure you write small. Check to see if it's correct by doing it and verifying that you get 8 numbers. Go through and make sure it's dividing correctly. Translate the code or the number back to the front of your card. Okay? Mitch, how did I do with letter I? I have a 0, 1, 1, 0, 1, 0, 0, 1.
No, that's not what I got.
Alright, let me check to see what I did.
Like, could be me.
Yeah, well, doesn't matter, I'll just check it. So you took 105 divided by 2, right? And you have 52 remainder 1.
Yep.
And then you took 52. Divide that by 2, and you should get 26 remainder 0.
Yep.
And then you took 26, divide that by 2, and you have 13 remainder 0.
Yep.
And you take 13, divide that by 2, and you get 6 remainder 1.
Yep.
And you took 6 divided by 2, and you get 3 remainder 0.
Yep.
And then you took 3 divided by 2, and you have 1 remainder 1.
Yep.
And then you took 1 divided that by 0, and you get a 0 remainder 1. And then you took the 0, divide that by 2, and you get 0 remainder 0. So you have 0, 1, 1, 0, 1, 0, 0, 1. The problem with this method, it's you make a mistake up here, it trickles down, right? Because your next calculation is dependent on the last.
So is it safe to say that every number will begin with 0, 0?
Yes, unless you get exotic, like the letter in my last name is going to extend it. In fact, when ASCII first came out, it was originally 7 bits, and the reason why it was 7 bits is that we didn't have enough memory, enough transistors, enough storage to be able to handle 8 bits. So we decided to say, well, 7's enough. You guys remember the Y2K problem? The little Y2K bug?
No.
And that's a contributor to this, in a sense. They decided to just lob off the 19 when you're storing the year. And the reason why they decided to cut off the 19 is that would save them 2 bytes for every record. That adds up real fast. And the reason why they made that decision is, at the time, hard drive space wasn't as roomy as it is today. And it was extremely expensive, let alone processing power wasn't there. Because all these zeros and ones requires space to be stored and attention to be manipulated, if you will. So the more zeros and ones you have, what do you think happens? The longer it takes to process them. In fact, that's the difference between high definition and standard definition. A Blu-ray can hold more zeros and ones. If you can hold more zeros and ones, you can represent more things. When it comes to images, those more things are called pixels. The more pixels we can represent, the clearer the image. However, the more space we need, the bigger the index card. And if you need to manipulate them in a timely manner, like when you're watching a movie, 30 frames are being processed in 1 second. That's a lot of pixels. A lot of pixels. In fact, to give you an idea, it's probably about 60 million pixels a second. That means it's about 180 million bytes a second, which is about 1 billion bits a second. And you guys are spending minutes doing a letter. But the exciting thing about it is we taught electricity a language. That fascinates me. In fact, that's why I got into computer science. Because now we can take it to the next level, and the next level being is, how do we process data Because if we start understanding how we process data, then we can start manipulating that. Ever wish there was something you did that you could just erase from your memory? You know, maybe your first kiss. Just get that out of there. Forget all about it. Or at least erase other people's memories. Who knows? Maybe there'll be a pill that you can swallow. That'll go in there and see some of those proteins and decide to rearrange them so you saw it differently. In fact, how many proteins make up our DNA? 4 unique proteins. That's all. And aren't we starting to manipulate DNA? You can go pre-order your baby. Want blue eyes, blonde hair, 6 foot, big chin. Once we get the code breaking down, folks, and we can start manipulating it on the fly, if you will, changing it at the will. Like I said last couple weeks ago, when you understand something, you can manipulate it. And that's what we're doing here. We're understanding how computers process data. And if there's ever a time where the machines rise up against us, we'll be able to fall back to this and start manipulating. Let's think about this now. On the back of your index card, you guys probably have a bunch of zeros and ones and a division symbol going on, right? Next thing I'm going to have you do, it's going to be like the last thing, and then I'll go back and explain this whole activity for you, is I want you to take all your zeros and ones that you wrote up on the front of your card, and I want you to string them along. So this is what I'm going to do. I'm going to start a couple lines down, and I'm going to start writing 0, 0, 0, 1, 1, 1, 0. That was the first 8 bits. Give myself a little space. 0, 1, 1, 0, 1, 0, 0, 1. That's the letter I. And then I'm going to go 0, 1, 1, 0, 0, 0, 1, 1. And then my last bit. Alright, index card exercise is done. Now you guys get out, your notebook out, and let's start writing some notes, and let's start making sense out of this misery that we just got done finishing. If this exercise was to illustrate that I wanted to show you how information is being processed into a digital format, hence information going data, information to data, if you will, then everything that occurs into a computer, you probably should have experienced. In fact, we have an acronym that describes any computing device. And that acronym is, let me check this out. The letter I, letter P, and the letter O. I is short for input. P represents process. O represents output. So we have IPO. Now some people want to add another layer out here called F for feedback. I like keeping it short and simple. IPO. And by the way, if you're a business person, it's not the initial public offering. So it's not about a stock going public or a company going public. It's input, process, output. These are the 3 things that must be met to define what a computing device is. In fact, I like to always ask my students, is a television considered a computing device? Let's find out. Input. Give me an example of an input device.
HDMI.
No, we're not gonna touch that. No.
Okay.
Just the TV itself, not anything
The
extra.
remote.
The remote control would be an example of an input device. I agree with that. And some TVs are now getting webcams built into them. So yeah, I'm all good with that. And you can even connect a keyboard to them. So I'm still kosher. What is an input device? Anything you as the user to physically touch, to supply the computer with info. Well, I should be careful about that. Let's cross that out. Let me say data. We'll do that, okay? So it's not info, we'll say data. So you supply the computer, you are inputting data into the computer, okay? You don't care that you entered in number 3 to go to channel 3, correct? That number 3 is data. What you care about is what's on channel 3. Does that make sense? So the remote control would be an example of input device. In this exercise, can you guys give me an example of your input device? Pencil, right? Alright, the P is challenging. I'm going to skip over the P. We're going to go to output. Bless you. The output receives the processed data and sends it to or back to the user as information. You good there? Can you give me an example using your TV as an output device?
Screen, the
The
sound.
screen itself, the sound? Absolutely. What would your output device be?
The remote. So.
Hard storage. In fact, it's sort of a tricky question because you can read what's on the card, correct? But the card itself is holding the data. So you really can't be two things. That'll fall here. So, what is the output device? Using today's exercise.
Lead.
Lead in your pencil, very good. In fact, without that lead being there, when the light hits the card, there'd be nothing to reflect. So it'd just be a plain white card, correct? You see the idea? We see the lead because light bounces off of it, correct? So lead would be the example of the output that's on the card. Well, tricky, but nonetheless. What about P? The P is sort of like the triangle of the computer. This is the most important relationship. In fact, when you're buying or shopping for a computer or fixing a computer, you're always focusing here on the P. There's 3 components. The CPU, memory, and storage. We call this the Holy Trinity. CPU is short for Central Processing Unit. A lot of people like calling this the brains of the computer, the workhorse. Now, anytime you are going to take data and manipulate it into information, you will have a processor. Your televisions do have processors. Because the signal that's being beamed to that television, whether through the airwaves or through your coax or whatever the way you're getting television, is probably nowadays stored in a digital format. You good about that? Zeros and ones. This is that digital format. The processor has to manipulate that to tell you, or tell the screen, what colors to display, so that you actually get to see the image. You clear about that? In order to do that whole processing, that manipulation, the computer needs a workspace. Much like the desk that you guys are working on, it's an area set aside so the data is coming in, the computer can manipulate it by using some mathematical formula. In the process of doing that, the work has to be done somewhere. Using your index card, what would that be represented by? Where did you guys do all your work? You did it on top of the desk, but where did you do it at? Because it was stored. In fact, things are stored in memory. The back of the card, right? Is that where you did all your mathematical work? And when you look at the back of that card, it seems like a bunch of random mess, correct? That's what we call random access memory. Did you guys care about where it was ordered at? You did anywhere back there. But when you brought it to the front of the card, did order matter? Did the place matter? Absolutely. The back of the card was just a scratch area, a workspace. If you have a CPU, you automatically must have some kind of memory. In fact, most of the memory is built into the CPU when it comes to your television. But when we use our computers, we need some extra memory, which you guys call RAM, right? This relationship between the CPU and the memory is really important. In fact, did you guys notice you did all your work back there and you kept on flipping it around? Storage. This becomes the challenge. Can you guys, without any external devices, store your television shows on your TV? Well, Samsung has released a television that will now allow you to do that. In fact, they got so smart about doing it, you can plug in any external hard drive via a USB port, and you can now start storing your TV shows on that. Pretty neat idea, right? I mean, forget about buying TiVo, or buying a DVR, right? Or adding extra $10 a month from Time Warner's to be able to have that Paulson television. It only seems to make sense to me. I'm like, once you make digital televisions, they're all zeros and ones, correct? In fact, those zeros and ones that you guys wrote back on the back of the card were the same zeros and ones that you wrote in the front of the card, correct? The only difference was you gave this order. You gave it structure. You grouped them together. What do we call that? When we take all those zeros and ones and we put them together in a container.
Compression.
We haven't done any of that yet. Before that. So we spent last week doing this. They're files. A file is I'll use this word permanent, with quotations, permanently stored data on your storage devices. Now, the reason why I use the word permanent is that when the power goes off, you're going to lose it here. Because these two components use electricity. This component here could use magnets. And when the power turns off, the magnets are still active. Hence the word permanent. Does that make sense? The front of your card acts like the storage device. No matter what happens to the lights, which I'll demonstrate right. You can't read that card, correct? You need light for you guys to see those letters on this card. But did they disappear? So when the power went out, I know it sounds funny, it's like the old saying, if a tree falls in the woods and nobody's around to hear it, does it still make a sound? You could get philosophical on it. You'd be like, well, Nick, I really can't answer that question because I can't see it. If there's no light, can you see what's on the paper? Does it still exist? Right? So you guys can make a new philosophical question. But, do they magically appear when I turn the electricity on? They're there. They didn't go anywhere. They are permanently stored on your card, especially if you wrote it in pen. However, the idea is when the power goes off, is the file still being stored? Yes. To me, going back to TV, it's absolutely a no-brainer that you can plug in your USB hard drive on the side of your television and record TV shows. They are already processed, those zeros and ones. It's just a matter of them flipping the card over and writing it down. Right? So, right now, the TV's on a threshold. We're calling them smart TVs, but it's only a matter of seconds. that you guys will be able to store. In fact, does anybody have a smart television? Can you install apps on that?
Yeah.
Welcome to the new computer.
Your Netflix is not right
Exactly.
on there, Amazon and everything.
Computer is any device that meets the following: IPO. Input, process, output. If it is a computer, what can we do with it? Anything and everything. We can watch YouTube. We can watch Netflix. We can update our Facebook status. Correct? Because why? It's in this format. This zeros and ones. When a computer sees this zeros and ones, how do they know to display text? How do they know to display letters? How do they know to display sound? Imagine this Thursday, you guys come into class, and then on the board, I write 1,000,000 zeros and ones, and that's all you see. How would you know that's a picture of my dog? How would you guys know that that's a movie clip of last week's lecture? How would you know that's a sound file? How would you know it's an encyclopedia? How does a computer know that these zeros and ones must use ASCII to be processed?
The extension of the file that they were.
The file extension. If it ends with a TXT, the operating system says, I must go to this map, this table, and process this as capital letter N, lowercase I, lowercase c, lowercase h. What if, by chance, my file extension wasn't TXT, but rather, what would that be? Picture. What makes up a picture? Pixels. What is a pixel? That's a pixel. The question becomes, is how many of these zeros and ones represents that little dot? Let's rewind. Let's take what we've learned and let's apply it. This is what we did when we learned number systems. We started with decimals, something that's very comfortable with us. And then we learned the rules of counting, correct? Then we can count other number systems. Alright, I started with letters. Very simple. I use them every day. To learn what? That a single letter requires 8 bits, which we call 1 byte. So 1 byte equals 8 bits, or 1 letter. The question is why? I always ask you guys, why is it 12 inches in a foot? Why not 10? Why is there 5,280 feet in a mile and not just simply 5,000?
That's a good question.
Because there is.
Because there is, that's my answer. Thanks for stealing that, Morgan. Just like, why is there what, more hot dogs than there are buns or something like that?
Yeah.
Well, there's a good answer to that one. It's because all you crooked business people. You make more money, right? There's what? More hot dogs than there are buns. So let's just say that if I go to buy buns, I gotta buy 2 now. 2 packages of buns. And all I need is 2 more extra rolls. Now you made an extra $5. And that's what happens to us all the time. We go, so we got all these old hot dog buns that we have to throw out to the birds because they expired. Because all we need is 10. I'd pay extra just to package you guys 10 rolls, please. So why is there 8 bits in a byte? Wasn't always like that. And we have since expanded this. We have the system called Unicode, which can take any letter known to mankind, any symbol, both past, present, and future, and be able to handle it. ASCII's designed for America. If you try to apply it for the Mandarin language, they'd be screwed. Because there are well over 256 unique symbols that make up Mandarin. So we had to add to it. By adding more bits, we can represent more letters. We simply said 2 raised to the power of 8 is more than enough to handle all of our symbols. 2 raised to the power of 8 is 256. That means I can handle 256 unique symbols. Question becomes is, what about color? I love screwing around with my dog. We have this dog whistle, and there's nothing more better than just to whip that thing out and blow into it, because I can't hear it. But my dog, he gets pissed off when it goes. And he could be miles up the road. I blow on that whistle, and it comes right to us, because he knows what happened, he doesn't, right? I love that. I love, as I get older and older and older, I get deaf, and it's hard for me to hear things. My room is on the first floor, and there's people that live above me. They get up at 5 o'clock in the morning. Inadvertently, I get up at 5 o'clock in the morning. Why is that? They're loud as shit. And I'm a very light sleeper. In fact, people try to sneak up to me when I was in college in the dorms, and I'd jump out of my bunk bed right on top of them, and they're like, what the hell? I was just going to bed. Yeah, I'm very light. I just, remember I told you I was a scrawny kid in my family? And he built these like prison reflexes. So I guard my food when I eat, old habits. And so, yeah, I'm really appreciating this lack of hearing that's happening. And people are telling me, maybe you should get a hearing aid. I'm like, yeah, I love it. I mean, turn the world off, I'm peaceful. And we all can accept that we have a range, a limitation. And I'm grateful for that limitation. In fact, the human ear can only hear about 10,000 frequencies. And it's not from 0 to 10,000. There's a finite range. Anything below that, we can't hear. And anything above that, we can't hear. So is it worth trying to capture everything that we can't hear? No, you'd just be wasting space, correct? So what about the eye? Folks, when you look at the color spectrum, actually the electromagnetic spectrum, we can only see a little sliver. And that's what we call visible light. And I'm so glad, because then I don't have to wear lead-based underwear. Because if I can see X-rays, or even gammas, I can see through your clothing. See through walls. And then the opposite's true too. If I could see AM or FM frequencies, because they're all the same thing, I'd be constantly dodging and ducking. Because these airwaves, as you guys want to call it, isn't really air. It's just free electrons bouncing all over the place. And you could see them if they were in our range of visible lights. So the question is, how many colors can the human eye see? You guys all experienced this. You went through some kind of color testing. Just like you went through the hearing testing. We put on the headphones, you had to raise your left hand and your right hand and such. And they went through all the frequencies. Thank you for being our guinea pigs. Throughout the 80s and the 90s, we were collecting data. And we asked our question, how many bits do we need to represent color? And the answer became, the human eye can see about 16.8 million colors. And that is a fraction of the electromagnetic spectrum. A fraction. So how many bits do we need to represent color? 24. Now, you want to know the easy way of memorizing that? What are the three primary colors?
Red, blue, and yellow.
Yeah, you're right. But we're going to get rid of that yellow. In computers, we call it red, green, and blue. You guys seen that pop up from time to time? RGB. How many bits made up a letter? 8, right? A byte is the smallest unit of storage, correct? If you were to take 8 and multiply it by 3, what would you get? Why did I take 8 and multiply it by 3? Because how many primary colors are there? 3. So if I was to use these zeros and ones to represent color, all I have is a pixel and a third. Computers don't do very well when it comes to thirds. Okay? I have 1 pixel right here. This is the red shade of that pixel. This is the green shade of that pixel. And this is the blue. This is basically telling me how much red I need to add to it, how much green I need to add to it, and how much blue I need to add to it. And this is the reason why we love our digital computers. We love them so much, we are starting to become like them. The way we behave, the way we act, people are becoming so anal today. It disturbs me. I have students that obsess about missing a point. We used to be a society where it was really all good. Everything was understandable, and there's a lot of just gray, a lot of shades, a lot of acceptance. Now we just like to see things black and white. You're either for me or you're against me. We love digital computers because we can reproduce the same results over and over and over and over. Do I have any artists out there? Remember, the 3 primary colors are red, green, blue, right? Let's say you buy a paint of red, a can of red, a can of green, and a can of blue, correct? According to what we've discovered, you can mix any one of those 3 together to get 16.8 million colors. If you try to do that at home, and you get this beautiful blue that you love, a month goes by. Can you reproduce that beautiful blue when you made it a month ago?
Only if you wrote it down.
Only if you quantify it. And that is half a cup of red, maybe that's what this is, pint of green, and an ounce of blue. But there comes the problem. You have to take it and dip it into the measuring glass, then you gotta pour that in there, correct? And as you guys well know, there's always that residual stuff left over. So the answer to the question is no. This lecture I'm giving you guys right now will never be the same. I always tell students when you go to watch an old film-based movie, now that we're going digital, the first time was always the best time. Every time that film ran through the projector, it would get worn out. This is why they had second-run theaters, and they became cheaper, because the quality degraded. But you know what the best thing about those analog films were? They captured everything. All shades. Here, all I had is 24 bits. And I'm saying that's enough to represent 16.8 million colors. There are more colors than that, and some people can see that. Translation. Remember the old 1 megapixel cell phone cameras? What happened when you guys went to go blow those things out to make a poster out of them? What happened to the quality?
Distorted.
What did we have to do to fix that? Increase the number of pixels, correct? More pixels, better clarity, better resolution, but what about space?
Take up a lot more
It's
space,
a lot more space. What about processing power?
slower.
Need a lot more processing power. Analog films. You guys can stretch that to the moon and you won't lose quality. Because they captured everything. Digital, it tells me exactly to turn this switch on or off, off, on, off. Very predictable. That's what we like about it. Do you see in this case, I needed 24 to represent one dot of color. When you have a 1 megapixel camera, how many pixels are there? What's the meg stand for? 1,000,000. That's 1,000,000 pixels. How many bytes should that picture be? How many bytes should that pixel be? Or that picture be? Oh, remember, it's 3 bytes to store 1 dot of color, right? Here's 1 byte, 2 bytes, 3 bytes. So 3,000,000 bytes. We give that a special prefix. What is it?
So MB.
3 megabytes. MB. Mega meaning million. Bytes is what you guys are now discovering, correct? Now you might tell me, Nick, you're full of shit. And you're right. Because if the file format is a JPEG, it's not going to be 3,000,000 bytes. Because a JPEG is a compressed file format. And what do? Look at all these zeros. Maybe what I'll do is I'll write, instead of storing 4 zeros, 4-0. And maybe I'll store 3-1. Do you see how I'm making it smaller and smaller? That's one way of compressing it. And maybe what I could say is, you're not going to notice if I just alter the shade of this color. We're assuming that if you have the world's greatest eyes, you can get 16.8 million colors. But we'll tweak that to the point that we can get that file to a more manageable size. An uncompressed file format when it comes to images is called a bitmap. I wonder why they call it a bitmap. They map all those bits to color.